Okay, hello everybody. My name is Nicholas Dwork. I'm an assistant professor at the University of Colorado. I work on accelerating MRI, trying to make MRI scans faster. And today we're going to be talking about a new way to do that. I'm going to try to develop the whole problem on stream, and we'll see how this goes. So we're going to start with some background, and for that, I'm going to bring up my iPad. Hmm. Well, as you can see, everything is going swimmingly so far. There we go. Okay. So first we're going to talk about MRI. I have a whole series of lectures on MRI. I'm going to put links in the description below, and you can go and watch those lectures to get the basics. But let's say we have a patient, we're staring down at the patient from the top of his head, so this might be the head, and then this portion here might be the shoulders or something. It's just meant to be a representative drawing. There are going to be coils placed around this patient, and each of these coils is going to sense data from the patient from a disparate vantage point. So the patient we're going to represent as X. We're only going to be looking at a 2D slice. So X is a complex 2D array of size, let's say, m by n. Each coil will have a sensitivity map associated with it. So for example, the first coil is going to have S1 as its sensitivity map. It too is a complex array of the same size, and by n, we're discretizing here. In reality, the coil senses on a continuum across space. But here we're going to just discretize it and assume it's a 2D array. The same is true for all coils. And we'll say there are capital C coils. Each of them is a complex array of size m by n. MRI is a Fourier imaging modality. That means it collects data in the Fourier domain. And so the first coil, the data of the first coil, is going to be a vector B that is equal to D times the discrete Fourier transform, which we'll represent as F, times the sensitivity map of the first coil times X. And here, D is a subset of the identity matrix. And it isolates which data samples were collected. And so, of course, we have these for all coils, capital C coils. I'm just going to check on the stream, make sure that I'm in the right position, and looks like it's going okay. Okay. So we could rearrange this into a giant matrix system. We have our vector x. Then we can make a block column matrix of the sensitivity maps here. Each of those sensitivity maps, each coil's image, SIX, gets Fourier transformed like so. And then each coil collects the same data at the same frequencies in the Fourier domain. So we make a giant diagonal matrix D like so. And this is going to equal the column vector B1, B2, etc. Okay. So then this is an overdetermined linear system. Or if D were the identity matrix, it would be an overdetermined linear system. If you reduce the amount of data collected, if you make D smaller, then you start losing numbers of equations, and so you get closer to making it just a full rank system or an underdetermined system. But if you remain overdetermined, though you don't collect every Fourier value in the m by n array, then you can solve for x by the following. I'm going to call this capital D. I'm going to call this capital F, and I'll denote it with a little tag right there. I'm going to call this S, capital S, and then I'm going to just call this B. And so we could find x by solving the following least squares problem. Minimize D, F, S, x minus B. And this is often a large system. DFS has many rows to it. So if it's small enough to be stored in your computer's memory, then you can solve this with whatever, SVD or QR decomposition. If it's larger, you can solve it with LSQR. And we're going to call this sort of approach model-based reconstruction. Great. And so it was largely a paper with the title, included in the title is sensitivity encoding. By Prusman, who recognized this way of reconstructing the MRI image X and reducing the amount of data that needed to be collected. And so this is one way to accelerate MRI, because you don't have to collect as much data because you have multiple coils, which makes the system overdetermined. There's a whole other way to accelerate MRI, and that's what we're going to talk about now. So this region that I'm drawing here is the Fourier domain, also known as K-space in MRI. And it'll be, so this is going to have m rows, and it'll have n columns. Okay. So with a single coil, in order to reconstruct an image, the conventional way to do so is you collect all mn data points, and then you just perform an inverse discrete Fourier transform, and that gives you a good image, highly diagnostic image. But then if you have multiple coils, each of these solid points represents a spatial frequency, a k-space location, that is collected by all coils. So each of these points represents a vector of C. Right? What if we don't collect some of these points? Let's say, for example, I don't collect that point. Oops. I don't collect that point. 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 And so now these are absent. And we have data around them. How can we estimate the value, the missing value at this location here? And the answer to this question comes from the papers that introduced Grappa and SPIRiT. One of the authors of Grappa was Sodikson, and one of the authors of SPIRiT was Lustig. And what Grappa realized is that I'm going to just zoom into these 9 points here. So I'm going to draw them again right here. This is our missing data value. What Grappa realized is that we can take a weighted average of the surrounding points to estimate this missing value. So if we call this K11, K12, K13, K21, K22, we don't know, K23, K31, K32, K33. And we call these weighting coefficients W11, W12, W13, W21, W22, there isn't one, W23, W31, W32, W33. Now, I'm pretending that these are scalars, or perhaps you're envisioning that these are scalars, and so you might think that you would just take the weighted average, but actually remember that each of these black dots represents a value from each coil. So if we have 8 coils, then each black dot represents a vector of size 8. And so actually each W vector as well represents, each W represents a vector of size 8 as well. And so what we're going to do is we're going to take K11 dot W11 plus K12 dot W12 plus plus K33 dot W33. And that is approximately going to equal K22. So Grappa realized that there's this linear relationship between the nearby sampled points and the unsampled point. And so you can go about, if you knew the averaging coefficients, all the W's, then you could go about solving for the missing collected data. And since you didn't have to collect as much data, since you could estimate them, instead of collecting them, this would reduce the amount of data, the scan time, because you could collect less data in a faster amount of time. So then the natural question is, well, where do these averaging coefficients come from? And the answer is this is our K-space again. And again, perhaps I've drawn these as though we collect all of them, but of course, maybe we don't collect an entire row. So where do these weighting coefficients come from? Well, we're going to choose a center region, a region at 0 frequency, centered on 0 frequency, and we're going to fully sample it. People often call this fully sampled region the auto-calibration region. And so here we could say to ourselves, we need these coefficients, we need these linear coefficients, and we're going to assume the linear relationship that we decided on before, this one here. But note that we know the answer now. And so rather than having to estimate this middle value that is uncollected, we know the answer for the auto-calibration region. And so this sets up a linear system in the unknown W. And as long as you collect enough auto-calibration points, it's an overdetermined linear system, and you can solve for the coefficients W. Let's check on chat. I'm sure that we have a huge audience attending, and they're just all staying quiet. Nope, I'm the only one in here. Am I deterred? Absolutely not. Okay. So that's how Grappa works. You find these linear coefficients from the auto-calibration region, then you go through K-space and do the interpolation to fill in all the missing values. And you fill out K-space, and then you can perform the inverse discrete Fourier transform on the data of each coil. And then that gives you an image for each coil. And then you can reconstruct, you could combine those images using various techniques, which we'll talk about when we get there. SPIRiT extends the Grappa approach And the difference is, I'm going to zoom into these points now. SPIRiT's going to assume we collect all nearby values. And it's going to say, so it's going to do the interpolation here at this point with these unknown values, but it's also going to do, well, I'll draw this in blue. It's also going to do the interpolation here, for example, for the known value. And all it's going to say is, it's going to take each of these equations for each k-space location. That becomes one linear equation. It's linear in the coefficients of k. It's linear in the Fourier values. So that becomes one equation. It's going to say find the missing values that minimizes the L2 norm of the difference for each of those equations, of the difference between the left side and the right side of each of those equations. And so this is going to be the purpose of this project. Previously, I told you we have this. And of course, minimizing the L2 norm and minimizing the L2 norm squared are the same thing, so that's fine. And now what we're going to do is add another term. And so for right now, I'll show it to you as a regularization term. So this is going to be another norm. We're going to add this as a regularization or a penalization term. And what we're going to say is, so I'm going to let, well, if I apply the SPIRiT kernel, if I do all of the interpolations to the quantity f, s, x, so these are the Fourier values, ideally, if we knew x correctly, if x was right, we would get back the same thing. Oops. So we're going to penalize the L2 norm squared of that. When you're using the L2 norm squared as a regularizer, this is a form of Tikhonov regularization, if you want the fancy word. Okay, so we could simplify this. This is the SPIRiT kernel. I'm going to subtract away the identity. And that gets applied to f, s, x. Okay, so this is our first goal for this research problem. To solve this to solve this optimization problem. And this optimization problem can be solved with known algorithms. In particular, this one can be solved with LSQR. How? Well, we can rewrite this as the compound matrix D on top, the SPIRiT kernel minus I on bottom. That gets multiplied times F, S, X, and then B on top, 0 on bottom. Those are equivalent problems. Oh, I forgot the lambda. Now there's always a question, is this lambda or lambda squared? Square root of lambda. Let's see, if it was just lambda, it'd be lambda squared is equal to magnitude lambda squared. What's going on? Okay. This needs to be moved over a little bit more. Right here goes square root of lambda. So that one, if we were looking at these equations differently, and lambda were inside the norm, we would have to square it to take it out. Yes, that's square root of lambda. Okay, fine. I don't know how to explain that any better. So this is actually just a least squares problem, and so this can be solved with LSQR. Okay, so like I said, our immediate goal is to solve this optimization problem. And the hope is that by incorporating the additional information of this regularization term, we can reduce the amount of data even further and still get a high quality image out. So step one is to solve for the linear coefficients W. Now, you might remember when I drew these pictures earlier, why am I just using samples 1 away? What if I use samples 2 away? Well, you could do that as well. And so we call that changing the size of the kernel. So these pictures that I've drawn are for a kernel that's 3 by 3, but you could have a kernel that's 5 by 5, 7 by 7. We typically make them odd so that the point that's being estimated has the same number of points on either side of it. So we have to code this up. We're going to have data, right? We're going to have to go about creating the linear system, and then we're going to solve the linear system, and that'll give us the coefficients W. Okay? I'm going to do all development in MATLAB, and my development is going to include functions that I've already created. They're available in the dworklib GitHub library that I've released. It's just always been out there. And boy, oh boy, does it take MATLAB a long time to load. We'll call this project SPIRiT-Reg. Maybe SPIRiT-Reg? SPIRiT-Reg. Got something here called sense grappa. Oh, that's the name of this project. That is a fancy picture. ChatGPT made that for me. Okay. SPIRiT-Reg, great. We'll call this MRI Recon SPIRiT-Reg. It's going to take K data as input, and it's going to, oops, been coding a lot in VI lately. It's going to output an image. And that's all it's going to do. So you might say to yourself, if you're familiar with MRI, you might say, what about a non-Cartesian trajectory? What is K data exactly? So here, K data is going to be a matrix, complex matrix of size m by n by c, where c is the number of coils. I'm going to assume Cartesian sampling, so uncollected data will have a value of 0. Maybe I should make this larger. Maybe I should code in VI. This is like quite difficult. Oh, there we go. Just had to use the mouse. Okay. So let's find out which sample points were collected, shall we? So this is saying we're going to take the magnitude of the K data, and this does each point in the array individually. And then I think this says take the maximum in the third direction, and if set the sample mask equal to 1 whenever that maximum is greater than 0. Let's make sure that's right. Yeah, okay. Look at that. What is that, like 3 lines of code? We're racing along here. We're also going to need the size of the auto-calibration matrix. And we're going to need the size of the kernel. Let's call it W size, let's say. The output is going to be complex, I think, in general, depending upon how we reconstruct the final image. But like I say, we'll get to that later. If W size is a scalar, then the kernel is assumed to have size W size, W size. So it's just the same in both directions. Great. MATLAB has an input parser. It has something that helps you deal with inputs. But we don't have any optional inputs yet, so we don't need this yet. I shouldn't have included it. Okay. Okay, great. We've got the sample mask, so we know which samples to collect. And so you could search through the files in dworklib if it's included in your path. Maybe I should show you guys where dworklib is. Right there. github.com/ndwork/dworklib. So these are my files. I've been working on this for a very long time. I hope it's useful. It's useful to me. So I'm going to look for the function called crop data. I'm going to open crop data. This is its prototype. So I'm going to crop k data to be the size of ACR. And let's make M and C. Can I do this? I'm always doing this sort of stuff. The point of developing on stream is to show people how someone like me develops, or actually just me, how I develop. And so I'm often doing things like this to see if I can do code the way I'm thinking. Sure enough, I can. Great. So we've got C. We aren't yet using M or N. That's fine. All right. Shouldn't have called this art. Oh, I should have called this ACR. Now we have the auto calibration region for all the coils. And so ACR has size SACR1, SACR2, C. Now we got to go about constructing the linear system. The easy way to do this would be just to use LSQR. But that would be slower. And I don't want to be slower. I want to be fast. So we're going to delete this code later, I suspect, but just for now, let's assume SACR is 3 by 3. So we're going to have one. This is the portion of the auto-calibration region for the first linear equation. Okay, so now let's not assume it's 3 by 3. By the way, you might be wondering, like, should the kernel be off the edge of the auto-calibration region? But I'm not going to do that. I'm just going to keep the kernel. I'm only going to create equations to include in my linear system for those points where the kernel is completely enclosed within the auto-calibration region. Okay, what do I call this? Like ACR1? Sub ACR? Sure, let's call that sub ACR. Just checking on the stream. Okay, this is going to work. So for I equal 1 to n, for j equal 1 to m, and j plus. One thing that takes a lot of getting used to, especially if you come from other programming languages like C, which is zero-based. In MATLAB, everything is column ordered, and everything is one-based. I suspect we'll be able to speed this up later, but for now, this is what we'll do. We're going to make a triple for loop. That won't be slow at all. Okay. Now the I should have looked at this. Okay, so if SACR is 1, 2, that's a column, so we need to put a transpose here. That makes this a 3-element row vector, and life is good. Okay. And we, of course, do not want to go to M and N. We only want to go, it's not this, but here's better. That's what it would be if, so ij, or ji rather, is the coordinate of the center of the kernel. But we've already said that we are not going to let the kernel slide off the edge of the auto-calibration region. So we need to go like minus SACR divided by 2. Let's see if that works. This doesn't. I should say that right now. Okay, so first things first. We're going to check the input parameters for stuff. And so now what? I'm going to require that a 2-element array of odd, W size is either scared a 2-element array of odd values that specifies the size of the interpolation kernel. So let's make sure it's odd. If max, or if min mod W size 2 is less than 1, and there's an error. W size elements must be odd. So MATLAB's giving me a warning. I don't quite understand it. So if W size is 4 or 5, that's not what we want. I'm going to take mod W size 2. That gives me 0, 1. And the min of that. Oh, I see. I needed the less than 1 outside of the min. Okay. Sure enough, that's true because here W size is 4 or 5. And if we go to 7, now it's false, and it won't give us an error, and everything's okay, and life is good. Okay. I should have mentioned, but didn't, that there are entirely different interpolation kernels for each of the coils. So you might have thought that the interpolation kernel was W size 1, W size 1, size 2 times C. You might have thought that. But that's only the interpolation coefficients for one coil. So we need one of those sets of vectors for the interpolation coil for the interpolation of each coil. And then there's going to be a -1 here because this -1 is to take away that point in the center that we're trying to use the interpolation coil to estimate. So instead of doing MRI Recon SPIRiT-Reg to begin with, we're just going to do MRI Recon SPIRiT. We're just going to do SPIRiT reconstruction. So this first step here, this first stuff we're doing. This is going to be to find the interpolation coefficients, W. Once we have them, we're going to use the interpolation coefficients to estimate the missing data. Okay. So going back to this, now we know that SACR2 and SACR1 are both odd. So what is SACR2 of 2? Or divided by 2 rather? It's 1. So let's say, what's 5 divided by 2? It's 2.5. Great. Do we want 2 or 3? So if the interpolation kernel was size 5, the value in the middle would be 3. So we want the ceiling. The index of the value in the middle would be 3. Let's say the ACR is, let's say SACR2 is, I don't know, 17. Well, this is not, I keep making mistakes. It's actually W size, not ACR. That doesn't make sense. All right, we figured out this one, so let's ride that train as long as we can. Now here's the question. How much do we subtract? So if the size of the ACR is 10, here's what I'm doing in my head, okay? So you have an array of size, whatever. I guess size 8. And we're going to have a kernel of size 3. Okay? So the first location is going to be here. What's the index of the middle location of the kernel? Well, it's going to be 2 because this is a 1-base system, remember? So this is 1, this is 2, this is 3, 4, 5, 6, 7, 8. So 3 divided by 2 is equal to 1.5, and then the ceiling of 1.5 is 2. Great. What about at the end? We've got 8, subtract 1.5, right? That's 6.5. So we want this to be 7 because that's the index of the center. How do we do that? We're going to take 8 minus the floor now of 3 divided by 2. 3 divided by 2 is 1.5. That's, this distance. And we only want to subtract 1. So I think that's the answer. Now this goes through the portion of the ACR where the kernel completely lies within the ACR. What I'm struggling with now is that this includes the center portion that we're trying to interpolate with the linear coefficients. So we have to get rid of that. Or do we? We have to get rid of it in some sense. We could either eliminate it from this array, or we could set its value to 0, and then when it gets multiplied times w, we would remove this -1, and then we'd eliminate that value of w afterwards. I guess it doesn't really matter. We got to get rid of the thing anyways. I need to buy my mom a Christmas gift. So let's find the index of this point to remove. So for the first coil, it's just going to be, going back to QuickTime, I think I'm going to leave it up. Okay. Is this still working? Do you guys see this? I guess you do. I like the dots nicer. This x, so what is the, for this one, it would be 3 plus 2, right? 1, 2, 3, 4, 5. Let's say we had a 5 by 5 kernel. Running out of space. This is the index of the point we need to remove. I'm assuming it's the first coil now. So now it's going to be this, right? 5 times 2 plus 3. So if we call the size of the auto calibration region m by little n. Then we need little m times the floor of n over 2 plus the ceiling of m over 2. Now what if it's not the first coil, right? We're going to add, remember it's a one-base system, so we need to take the coil index minus 1 times mn. So, because if it was the second coil, for example, we'd need this index into the second slice of the array. And so we'd have to like move ahead by mn. And this is the answer. Now I want to use little m's and little n's. I have to do this. Wait a second. No, still convinced. No. No, I did that totally wrong. Totally wrong. Let's try again. Okay. It's simpler. Much simpler. We know the location of the center of the kernel, right? So let's say it's here. Well, its location is Ji. Okay, so the value we want is J plus I minus 1 times M plus C minus 1 times Mn. Forget this part for now. If the value were here, I would be 1, J would be 3, and that would be exactly the value we'd want. So this would go to 0. If C were 0, if C were 1, this would be 0, and then we'd get J, which is exactly what we wanted. Over here, what do we want? Well, we want this many points plus this many points. Well, this many points was J from before. This many points is J from before. And this many points is I here is now 2, so it's going to be 2 minus 1, 1 of the number of columns, the number of points in each column, which is m. That's how it works. Okay. The point to remove index is J plus I minus 1 times M plus C minus 1 times M times N. Note that the point to remove will never be 1 or the last element in the array. So now we could just take it out. Sub ACR is equal to sub ACR from 1 to point to remove index concatenated with sub ACR from point to remove index plus 1 to end. These are the data values that we are going to use to interpolate. Now I'm forgetting in SPIRiT, actually, if we actually use the other coils at the spatial frequency in, data that we're interested in. I don't know why we wouldn't, but it's been a while since I thought about this. We're going to come back to that at some other point to do. Do we use the data at the center of the coil, at the center of the kernel from the other coils? Okay. So this matrix, the system matrix that we're going to be creating, forget about the number of rows right now. Let's just think about the number of columns. The number of columns is going to be the number of elements in this array. And how many elements are there in that array? Well, it's the number of elements in the ACR minus 1. So it's m times n minus 1. How many rows are there? Well, there are the number of rows equal to the number of equations. The number of equations, there's one equation for each ji coordinate. So that's what we need. I think this is going to be this is either n minus floor or ceiling W size. And then it's going to be that times we need a vector for the other side of the linear system. Okay, so A of, here, I'll show you the simple way and then I'll show you what I'm going to do. So I've now put these values from the ACR into A. And B of A index is going to equal to if we hadn't removed it, I could have just done sub ACR point to remove index. So I'm going to do that here, then remove it, then plug that into A. That is our linear system. Oops, forgot. And then A index is equal to A index plus 1. For whatever reason, MATLAB does not have the plus equals operator. That will probably never change, and I have no idea why. And then W for this coil is going to equal A backslash B. That's how you solve the linear system when you can store it in memory in MATLAB. That minimizes the L2 norm of A W coil minus B. And then W is equal to reshape W coil. Ooh, no. Now we need point to insert, don't we? Do we? No. No. What am I thinking? Well, here's the thing now. We could think of W coil as a convolution kernel if we had a 0 at the point where we were going to multiply by the value that we were going to estimate. So that's what I'm going to do. Coil 1, 2, point to remove index. Ooh, this should be a -1. Zero W coil point to remove index +1 to end. And now I can store that as W. W size. Oh my goodness, I keep silly. This is because we need C, an array of size C in the third dimension for every coil. We had that discussion earlier, didn't we? Oh, W is not stored as a two-dimensional array like that. Well, let's change that. Get rid of -1 because that's this 0. W size, yep. Let's keep checking on stuff. If num L, I forgot to do this earlier, W size equals 1, I'm going to make it a 2-element array. There's an is scalar. Did you guys see the message? It says, to improve performance. Would that really improve performance? If that does improve performance, why doesn't MATLAB just do the same thing in the background after interpretation? And then it wouldn't improve performance. But whatever. So we haven't needed the sample mask yet. We may not. Let's get rid of it. We haven't needed n by n either. Or little n? Are you joking? I used little n right there. wants me to put a comma here. What's the error message it's giving me? Best practice is to separate out variables with comma. Okay, so I'm going to keep the I'm going to tell it to stop giving me this error warning here that we're not using capital M and N. I think I'll use it later, but if I don't, whatever, it doesn't matter. I really think we use these center locations from the other coils, so I'll check into it at some point probably. And now we have our our linear coefficients. That's as far as I wanted to get today. This is going to be more challenging than I expected because this is a 4-dimensional array. It's a 3D array for each coil. We could load some data and see if this runs at all. Oh, this is a weird one. Not going to use that code. It's just a little bit weird. I guess I could. Just a little bit weird. Let's see a different code. All right, so bunch of parameters, blah, blah, blah. For data case index, we load the data and the true recon and the noise coordinates. Oh, I forgot. So we're going to take all of this. We're going to delete most of that. Going back to our SPIRiT-Reg code, new script, run recon SPIRiT. Reg. SPIRiT-Reg, sure. Even though we're just doing SPIRiT right now. So apparently we have 9 data cases. That'll be fun. Start with 7. So this is a load routine that I've already created for another project. I'm just going to use the same load routine. That's what I'm doing here. This is for parallelization, which we're not doing yet, but you could easily see you might imagine this code could be parallelized, for example. Right, this is embarrassingly parallelizable. And we might do that, but not right now. Should be kdata. I forgot to actually include the load data case. Where is that? So you see what it does. You know, it uses read routines to load data from somewhere on my computer. That's it. Case 7 is I think this is a brain. Let's go for an ankle. Case 9 is an ankle. Okay. So this data and the read routine was released with one of my recent papers. Let's see which paper it is. This one, accelerated parallel magnetic resonance imaging with compressed sensing using structured sparsity. Co-authors Jeremy Gordon and Aaron England. So you could get the code here. Load data case, look at that. Let's add some more parameters up here. W size will be 5. And SACR will be, 17, let's say. Let's do the same thing with SACR, where if it's just a scalar, and we make it into a 2-element array, seriously. Just a moment. And now, believe it or not, we can actually see if this thing runs. unrecognized function or read variable read MR raw data. This means that there's something in my path. I'm going to fix that off stream. And I think that's where we're going to end today. So I hope you've enjoyed this. We've got a good start. We've got the interpolation coil, the interpolation coefficients. That's basically halfway there to SPIRiT, which is halfway there to SPIRiT-Reg, which is halfway there to a new method for accelerating MRI. We're like 1/8 of the way there. It's amazing. Thank you all for your attention.